Hello, my name is Shinwoo An, and I'm going to talk about an approximation algorithm for the geometric multi-matching problem. So this is a joint work with Eunjin Oh and Jie Xue. So first of all, let me introduce a well-known geometric mean-cost perfect matching problem first. In this problem, you're given 2 point sets, red points and blue points, and we're going to compute a perfect matching, which is just pairing between red points and blue points. Then each weight of the pairing is defined by the Euclidean distance between 2 points, and the cost of the perfect matching is defined by sum of its edge costs. So our goal is to compute a perfect matching whose cost is minimized. So here is the exact solution of the mean cost perfect matching. And today, our main scope is on geometric multi-matching problem. So here, the situation is slightly different. So now we are given a 2 point set as well as a vertex demand function. And we are going to compute a multi-matching, which is an edge set that covers each vertex at least bs times or bv times. And the cost is defined as a similar manner. So here is an instance that red points, blue points, and demand function for each vertex is given. And this is the resulting multi-matching solution. You can see, for instance, in the middle blue points, that guy are connected to 3 red guys here. And this geometric multi-matching problem is quite similar to the graph version well-studied B-edge cover problem. So in this problem, we are now given a graph and a demand function. And our goal here is to compute a minimum weight edge set E prime that covers each vertex v at bv times. So this problem has already widely studied. And so far, there are either m to the 2 over 3 time exact algorithm or near linear 1 plus epsilon approximation algorithm. Here m denotes the number of edges. And observe that we can formulate a BH cover instance for our multi-matching problem by designing a complete bipartite graph on S and T whose edge range is defined by Euclidean distance. And therefore, previous graph algorithm results implies either n cubic time algorithm or near quadratic time 1 plus epsilon approximation algorithm for this problem. And surprisingly, there is no non-trivial results beating this trivial corollary barrier. And here is our results. So given a 2 point sets S and T, let large B denote the summation of the degree demand function. Then our first result is 1 plus epsilon approximate multi-matching algorithm running in time near linear in B, not in a n quadratic time. And for the second result, if the B function is specifically identical to 1, then the running time becomes 1 over epsilon poly times n log n time. And here are some remarkable points. So since the solution size is B, there is trivial lower bound for this problem. And also, in the special case of B is identical to 1, the problem has alternative name, a geometric many-to-many matching problem, and we improved the best known algorithm for this problem by shaving this huge epsilon factor into 1 over epsilon's polynomial time. So basically, our geometric multi-matching algorithm is based on the efficient implementation of the BH cover algorithm using some geometric new ideas. So let me briefly review the previous graph BH cover algorithm. So their first step is make a reduction to the F matching problem. So here's the difference. In the BH cover problem, each vertex should be covered by at least BV times, whereas in the F matching problem, each vertex should be covered at most FV times. So the reduction is quite simple. Just take the subtraction of degree V and BV. So here is an illustration of K44 example. Just make a reduction by taking FV as degree V minus BV. And suppose we somehow get an F matching solution of this instance, then we take the complement of this F matching, and this will lead us to give an BH cover solution. And it's not hard to observe this reduction is safe. But however, the issue is that we are addressing an approximation field. So whether it's true, so if we have an 1 minus epsilon approximate F matching, then does its complement is 1 plus epsilon approximate BH cover or not? So sadly, this does not hold in general. But luckily, if our F matching M has also involved with dual variables for each vertex, and if its dual satisfies certain condition, then we know its complement becomes a non-plus epsilon approximate BH cover. So very roughly, this condition is approximate slackness condition, where for each edge uv, the summation of ZU plus ZV of dual variables are identically should be an HUHWUV, but since our working in approximation field, we allow some affordable error, namely epsilon times WUV here. So now you are sufficient to address F matching problem. And to do it, they design two technical ingredients, an augmenting path framework and a scaling algorithm. First, an augmenting path framework is starting from an empty matching edge set M. We're going to flip augmenting paths repeatedly. So here is what it means. An augmenting path is an alternating path between matching edge and non-matching edge, but it should start and end with non-matching edges. So here's an example. So the flipping means we change all non-matching edge into matching edge and all matching edge into non-matching edge. You can observe that the total size of M increases by 1 due to the flip operation. And then scaling algorithm is as follows. So algorithm works for log W scales, where W denotes a maximum match rate. And at the beginning of scale I with current matching M, we set current gap delta I as epsilon W over 2 to the I, and we round down each edge rate accordingly. So the meaning is as follows. Recall that we allow some affordable error from the approximate slackness condition. So each edge UV may have epsilon times WUV of error. And in scale I, we are going to compute a partial matching whose affordable error is only about delta I. So in this manner, the scaling algorithm works as follows. So we are going to run a 1 over epsilon time iterations. So in each iteration, we do the following. So first, we find a set of edge disjoint augmenting paths and cycles as many as possible, and then we flip them to increase the matching set size M. And then we change the dual variables accordingly to maintain the approximate slackness condition. So this is quite efficient for the graph version, but in our multi-matching problem, there are some complexity issues. So first issue is that in the augmentation work, they run the DFS type search. So this takes linear in the number of graph edges. But the problem is that in the geometric multi-matching version, the graph complexity becomes n-square. So this is worse complexity. So to resolve this, we design geometric tools to allow us to compute a DFS tree running in near linear time. And next, more involved issue is that the number of structural changes to M can be n quadratic. So this is as follows. So initially, M was an empty set, but at the end, its size becomes a quadratic. So to handle this, we are going to design a new idea, so namely a complement-based implementation to implement all data structures and structural changes running in only B time and space. So let me give some little details. So for the first part, the goal of the first step perturbation is to bound the spread of the point set into poly n. So here, the spread means the ratio between maximum distance and minimum distance between 2 points. And the second step, its goal is to represent all edges using non-overlapping near linear number of biclicks. And then we can store each biclick in only linear space. More specifically, its name is well-separated pair decomposition, which aims to divide the graph edges into n biclicks. So for each biclick, I'm going to denote this as a pair. The distance between 2 points in a same part of same points is quite smaller than the distance between opposite parts. The construction is also traditional, just recursively divide the grid cells into smaller ones and return them as a pair whenever they are well separated or not. And let's move on to second idea. So before suppose after the pre-processing, we adjust HUH inside the pair identically. So this is not dangerous because of our definition of WSPD. And then some intuition is as follows. So first, at the end, although the complement size has B, but matching itself has fairly large complexity. So here comes the idea of can you store and maintain the complement of the matching edges. But however, at the beginning, M was an empty set, so whose complement size is quadratic. And third, in the middle, both of the M and its complement becomes large size. So our idea here is the mixing two approaches, complement and exact, so appropriately. So here are some more details. The key technical function is about batch update. So given a pair of WSPD, suppose we know a subset S prime of T prime, which are currently unsaturated vertices. So here, unsaturated means its degree caused by matching edges is strictly smaller than the degree demand FV. And suppose we know a subset E prime of those edges, and then batch update will insert all edges of S prime T prime minus E prime, as many as possible simultaneously. So this is work as follows. So given a pair S and T, some guys may be saturated and some guys may be unsaturated. And we are interested in unsaturated guys S prime and T prime. So as a first step, we add all edges of S prime T prime biclick simultaneously. And of course, this will violate degree upper bound for some vertices. So we're going to remove some of those edges in a greedy manner to satisfy the degree condition. And here's the striking point. We are going to store and maintain those removed edges at E prime instead of storing the current exact matching edges. And we can observe that the complexity of this batch update takes linear in the size of S prime, T prime, and E prime. So here are some analysis why this batch update is efficient. So first of all, due to our construction, roughly speaking, all vertices become saturated after the batch update. So which means batch update occurs at most one times for each pair. And furthermore, since there are no unsaturated pairs after the batch update, then all remaining steps will compute and maintain augmenting passes of length at least 3. So this is quite important because our main technical observation is that if the total of all augmenting paths has length n list 3, the total structural changes to our matching set can be bounded to big O of B. So therefore, we can handle all batch update running in n plus b time, and using some nearest neighbor data structures on WSPD, we can also handle the remaining b times of updates running in near b time. So as a result, we can implement scaling algorithm efficiently. So here is our summary. So we obtained the first non-trivial algorithm for geometric multi-matching problem running in near b time. So as a main technical block, we implement the graph version BH cover algorithm efficiently, where the main structural issue comes from the large number of changes to M. We resolve it by our new idea of complement-based implementation. So here are some further works. So this problem has a lower bound b log n, but our upper bound is b log square n. So it would be interesting to try to match these bounds. And further, we are interested in applying our new complement-based implementation technique to other geometric type flow and matching like problems. So that's it. Thank you for listening.